Hello and welcome to this lesson. In this lesson, I want to look at some calculations that we find in particular topics. And I want to go through some calculations in the topic turning effect of a force. This is one of the topics whereby some students do find some challenges and you might benefit from the discussion in this particular lesson. So with me here, I have a few questions that I'd like us to address. Like for instance, this particular question here, where we are told that the diagram in figure 5 shows a beam of negligible weight. So you're going to neglect its weight. What that means is that the weight of the beam is so small compared to the forces which are acting on it. The weight of the beam is so small, so it can be neglected. If you are to include the weight of the beam in that calculation, it will not change the answer very much. So we neglect its weight. But remember, there are some questions whereby you will be required to consider the weight of the beam or with the weight of the object on which forces are acting. So let's continue. In that diagram, we are told that it shows a beam of negligible weight balanced by constant forces P and Q. Forces this P and Q. Derive the relationship between X and Y. Now, since this system is in equilibrium, it is in a state of balance. Since it is in a state of balance, we can apply the principle of moments. So when we apply the principle of moments, it's up to us to choose the point about which to take moments. This other student, you're supposed to decide the point about which to take moments. Normally, the point about which, the point that you choose to take moments should be such that it eliminates any other force which is acting on that system. And usually it is always the pivot. So I will take moments about this pivot. So it's always important to tell the examiner, take moments about this particular point. And then you decide which forces tend to turn that system clockwise about that point and which tend to turn it anti-clockwise. And it's clear that when you look at P tends to turn that system in the clockwise direction, like that. While Q, because of the way it is pointing, it will turn the system anti-clockwise. So the moment you decide the forces which turn the system clockwise and the ones which turn the system anti-clockwise, you are on your way now to write down the expression. You have said take moments about the pivot. So we'll say the force P times the distance X will be equal to the sum of the anti-clockwise moments. By the way, in this question, it's just there is just one force, there is just one clockwise moment and one anti-clockwise moment. So the distance from point P all the way to the line of action of Q is Y. So the moment you get that, it's just a matter of combining X and Y, putting the X's together and putting the Q's, the forces together. How do you do that? The best is to, let me use a different color. The best is, I want to get rid of Y from this other side. So I'm going to divide by Y here. So in which case now Y will cancel out, okay? The other thing I want to get rid of is P. So let me use another color to get rid of P. To get rid of P, the best way is to divide both sides by P. And again, you see the P cancels out here. So I end up with the expression X over Y is equals to Q over P. And this is what the examiner would be looking for 2 marks. It's just as simple as that. So here there were no numbers, and I hope you have understood how we have worked it out. Let's look at the next question. I just have 3 questions in this video. We are told that figure 9 shows a uniform bar in equilibrium. It's a uniform system. It's a uniform system. When you're given a uniform body, the examiner is trying to tell you that the center of gravity of that body is at its geometrical center. What do we mean by geometrical center? This is what? It appears to be like a bar of 5 meters. 5 meters. So if you divide 5 meters by 2, you get 2.5 from either end. That is where you get the center of gravity of that particular object. So the center of gravity of this object will be at this point. That's where I'll put the G. What is center of gravity? Center of gravity is the point through which its weight acts. So the weight will act through that point. Apparently for this diagram, the object is also pivoted at its COG. The object is also pivoted at its COG. It does not always happen that way, like we see in the next question. So it is in equilibrium, so that means I can use the principle of moments. Under the influence of two forces, determine the magnitude of force F. Determine the magnitude of force F. You can see that the line of action of F, it does not make 90 degrees with the 2.5 meter distance, because that one is a condition. When you're taking moments about a given point, you make sure that the force and the distance make 90 degrees. So the best thing to do is to try and resolve this force. We find its effect in this direction. You can see that if we had find its effect in this direction, then it means that the force that we are considering, which is now this force, will be perpendicular to the distance. So how best do we do that? We can just complete this right angled triangle like that up to that point, and then we come like this, and then we ask ourselves, what have we been given? We know the hypotenuse, we know this angle, we want the opposite. We want the opposite, which happens to be here. If we calculate this, we will have got this. So again, we use the SOHCAHTOA, and you can see the sine is the best trigonometrical expression to use. So when I get sine of 30, I'm going to get this side here, which I can call, let me call it x, for example. I'm going to get x over the hypotenuse, which is f. So that x is going to be equal to f sine 30. Sine 30. So that is the force that I want. So this one is supposed to be F sine 30 degrees. So I'm going to take moment about this particular point again in order to eliminate the effect, the moment due to the weight. I do not need the weight of that object. The beam might be, the weight of the beam might be negligible. Even if it is appreciable, then I've gotten rid of it because I've taken moment about the point through which the weight of the object passes. So when I do that, we're going to see that the 20 Newton force tends to turn the plank of wood clockwise, and it also tends to turn F sine 30 tends to turn the system anti-clockwise. All right. So let's take a moment about that point. So I'm going to put the equal sign here, and I'm going to say the clockwise moment is due to 20 times 2.5. That is how I get the clockwise moment due to the 20 Newton force. The anti-clockwise moment is due to F sine 30. So F sine 30 multiplied by this distance here, 2.5. And the 2.5 can quickly cancel out like that. I remain with F sine 30. Sine 30, if you check from your calculator, is 0.5000, or just 0.5 is going to be equal to 20, and you'll find that if you use your calculator well, you're going to get 40 newtons as the value of F. That is how you work out a question like that. What do you learn from this question? The examiner is trying to test, do you know that the force and the distance must be perpendicular to each other? That's what the examiner is trying to test. The other thing is this. Do you know that even if this object, this bar, had a weight that which acts through its center of gravity, do you know that if you pivot that particular bar about the center of gravity, the moment due to the weight of the object is 0, and therefore it disappears from the question? That is very important. Let's look at the next question. The next question is here, where we are told that figure 4 shows a uniform meter rule. Uniform meter rule. A meter rule is 1 meter. Like you can see, it is 100 centimeters here. 1 meter. Remember, 100 centimeters is 1 meter. So this is a uniform meter rule, meaning that at the 50 centimeter mark, the geometrical center of a meter rule is the 50 centimeter mark. After all, if you divide 100 by 2, you get 50. That is how they've gotten this point. This means that this point here is its center of gravity, and that is where the weight acts. And the examiner has given you on the diagram, the examiner has shown you that the weight is acting through the 50 centimeter mark, but this one is optional. They could leave it. They could leave it out. It's up to you to know that if you're given a uniform body, its center of gravity is at its geometrical center. If you're given a uniform object, its center of gravity is at its geometrical center. What that means is that if it's a given length, you divide it by 2. If it is a circle, you know that it is at its center, and so forth. So it shows a uniform meter rule of weight 1 Newton with 2 weights of 0.18 newtons and 0.12 newtons suspended from its ends. Determine how far from the 0.1 newton weight a pivot should be placed in order to balance the meter rule. So let's assume that we put the pivot somewhere around here. That's where I want to put the pivot. Let me change the color of this pen so that I can be able to see it properly. So I'm supposed to calculate how far from this weight do I put that pivot. So I want to make my unknown to be this distance here, to call it D. That means that this distance here from now the pivot all the way to the center of gravity will be 50 minus D, or 0.5 minus D. Everything I want to work out, everything in meters, right? That is what it means. Why do I need that distance? I will need to get the moment due to the weight of the meter rule. The other distance that I need is this one here, because there is this 0.12 Newton weight, and the whole of this is 1 meter. 1 meter minus, if I subtract D, I'm going to get this distance here. You can see all my distances now are given in terms of D, and once I solve D eventually, then everything will just be fine. So take moment about the pivot. I'm going to look at the sum of the clockwise moments. Let me say sum. I want to start with anti-clockwise moments is equals to sum of clockwise moments, like that, right? So the sum of the anti-clockwise moments will be, there will just be one anti-clockwise moment, and it is due to the 0.18 Newton. So I'm going to get 0.18 newtons times D is equal to, how about the clockwise moments? There are 2 clockwise moments. One of them is due to the weight of the meter rule, which is 1 Newton, times how far it is from the turning point or from the pivot. It is 0.5 minus d, plus, remember we have said there are two clockwise moments. What is the other one? The other one is due to the 0.12 newtons times how far is it from here? It is 1 minus d meters. So this is the expression that you must solve. Remember, this one will just give you 0.18 d. Over here you must open the brackets. 1 times 0.5 is 0.5. 1 times d is just d, plus, again you open the brackets here, 0.12 times 1 is just 0.12 minus 0.12 minus times minus d, you get minus 0.12 d. So here I'm going to combine. Of course, this one now gives me 0.18 d, no problem with that. This one and this one, this one and this one, first of all, gives me 0.62 minus 1. So I have added this one and this one, minus d minus 0.12 is going to give me minus 1.12 d. And then I will take this one to the other side, where I'm going to add it on to 0.18 d, and this is what will give me 1.30 d is going to be equal to 0.62, and then to get d I just need to divide 0.62 divided by 1.3, which I think I had done this one much earlier, and it was giving me 0.477 meters, which is this one was rounded up, therefore in centimeters it will be something like 47.7 centimeters. That one appears reasonable. 47.7, it should be around here, closer to 50. So that's how far that pivot should be from the 0.18 Newton beam. So those are some questions that you get from in turning effect of a force. Now, I've mentioned something about center of gravity. Center of gravity being very important when you're looking at questions to do with the turning effect. So I'm combining these two topics, turning effect of a force and equilibrium and center of gravity. Again, I have some questions here that I want us to consider in COG and equilibrium, and I want to go straight to the questions. Some of these questions are found in your course book, but that does not mean that when they are found in your course book that they are easy. In fact, it's important that you understand the questions in your course book before you go to any examination questions. So this one is a question in the course book. Let's just go through it and see what you were supposed to do. We are given a uniform metal bar. Uniform metal bar. Now you're getting used to that term, uniform body. What does it mean? If you're given the length of that bar, then you divide it by 2 in order to get the 50 centimeter mark. The 50 centimeter mark will be somewhere around here. The 50 centimeter mark, that is where the center of gravity is found, and that is where the weight of the object is. Remember, in the previous questions, we had always supported that object at its COG, so that we neglect the weight of the object. Not actually neglect, so that the moment due to the weight of the object becomes 0. But this time you can see that the pivot is not at its COG. Where a mass of 1.5 kilograms is attached at the 0 centimeter mark here. Calculate the weight of the bar. There's something else here. Yes, I think I've already seen that. So the weight, this weight is attached here, so we can get this weight as mg, which is going to give us 1.5 kilograms times 10 Newton per kilogram. That is how you convert mass in kilograms into weight in newtons, and you're going to get 15 newtons. So this is the force that is acting at this particular point, 15 newtons. So 15 newtons makes 90 degrees with this distance here. So it means we can take moments about that point and it will tend to turn the system in the anti-clockwise direction. How about the weight of the object? The weight of this meter rule is going to turn it clockwise about the same point. How far is it from that point? It is from the 20 centimeter mark all the way to the 50 centimeter mark, meaning that it is 50 minus 20, which is going to give me 30 centimeters, while this other one here is just 20 centimeters. 20 centimeters. So we take moment about the pivot, and we're going to say the sum of the clockwise moments, which is W times 30. I want to convert that 30 into meters, although it is not necessary, because what I do to the right, I also do to the left, so it is as if I never did it in the first place. So the clockwise moment is due to the W times this distance here, which is 30 centimeters. The anti-clockwise moment is due to the 15 Newton force times how far it is from there, which is 20 centimeters. Again, divide by 100 and to convert it into meters. This is what I'm saying. If you go ahead and multiply this side by 100 and this side by 100, you see we end up with a previous expression where the values were in centimeters. They were in centimeters. So that's why I'm saying it's really not necessary. So the left hand side is going to give me 300, while this one is going to give me W times 30, and I can see that if I cancel out, divide by 30, the weight of the object will be 10 newtons. Just as simple as that. What is it that we learn here? Number one, when you are told that a system is uniform, then remember to divide that system by 2 in order to get the point where its center of gravity is acting. Very important. And then the rest is just using the principle of moments. You identify the point where the system is supported and so forth. Let me just point out that if you are to look at the forces which are acting on this bar, if somebody asked you about that, you'll be able to see that one of the forces that is acting on the bar is the 15 Newton. The other one is this one here, 10 newtons. How about the pivot? Do you know that the pivot exerts a force on this bar vertically upwards? We call it the reaction. Supposing somebody were to ask you to calculate the reaction, how much will it be? Here you use the second condition for equilibrium. Which states that the resultant force on the system is 0. What that means is that the sum of upward forces, for example, is equal to the sum of downward forces. And the sum of upward forces is this reaction. The sum of downward forces is the W, which is 10, plus 15, which gives us 25 newtons. So there are 3 forces acting on that metal bar. The force exerted by the pivot vertically upwards, which is 25 newtons. The weight of the bar, which is 10 newtons. And the weight of the other mass at the 0 centimeter mark, which is 15 newtons. However, that one is not asked, but you can be asked to calculate it all the same. Let's look at another question in the same textbook. it's still in the topic center of gravity and equilibrium. A uniform meter rule, now you're getting used to this, of weight 0.9 newtons is suspended horizontally by two vertical strings P and Q, placed 20 centimeters and 30 centimeters from its ends, respectively. Calculate the forces or tensions in each string. So let me call this, of course, we know the tension is called F1 and F2. There's no problem with that. And then there is this other one, vertically downwards, like that, supported by two strings, and its weight, like that. How do we deal with a question like this, and yet there is no pivot? There's no pivot. You identify one of the points, and then you assume it is a pivot. Let's identify this point, for example, and you say, take moments about point A. You'll find that the force whose line of action passes through point A, its moment about that point will be 0. Okay? And then, how far is this from point A? How much is this distance here? Can we be able to get it? Given that this 0.9 acts at the geometrical center of this meter rule. This is the 50 centimeter mark. 50 centimeter mark. That means that this distance here is 30 centimeters. This distance here is 30 centimeters. If this one is 30, it means that this one here is 20. This is 20. So if we take moments about this point, you will find that the weight of the meter rule tends to turn it clockwise. The tension F2 tends to turn it anti-clockwise about this point. The moment due to F1 is 0 because the line of action of F1 passes through point A. So let's get our expression. Clockwise moment, of course, sum is equals to anti-clockwise moment. Okay. Clockwise moment is due to 0.9 newtons times how far it is from there. It is 30. And then the anti-clockwise moment is due to F2. How far is it from this point? 30 plus 20, which is 50. And notice that distances are always measured from the same point. Yeah. Don't look at this. You can see that it is 20 and then you end up multiplying F2 times 20. No, the turning point is this point. Right? So, in which case now F2 can be worked out. You can get F2. That one's easy. And then, when it comes now to getting F1, you will say sum of upward forces, which is F1 plus F2, is equals to sum of downward forces, which is 0.9. And since from part A you have worked out F2, you can clearly work out F1. Alternatively, you can change the pivot and say, take moments about point B. In which case now, clockwise moment will be due to F1, and anti-clockwise moment will be due to 0.9 Newton force. The moment due to F2 will be 0 in that case. So I think go through the video, look at the argument that I've tried to present in this particular video, and see how those problems are worked out. Then I have just one question for you. This one appears in the revision exercise. I'm calling it example 4, but in your textbook it is a revision problem. So go through that problem and see whether you are able to work it out. And let me know in the comments below whether you're able to work out that question. If you do not have the textbook, then just pause the video at that point, then work out that question, then see how it turns out to be. You can even give me the answer in the comments, and then I'll be able to respond and tell you whether it is correct or not. If you are still having challenges in the next problem, I can start with that. Otherwise, see you in the next video, where I'm going to look at calculations in another topic in our system of education 844.